Okay, we've seen how to construct a sine graph using compass and straight edge based on subdivisions of the unit circle, okay, of any circle. This is an unlabeled sine graph. There's no assumption this is a unit circle. We will later assume this, and we've already seen how that's assumed. We're going to move into more theoretical and more advanced ideas here in a minute. Now, we want to first of all consider how many subdivisions we've achieved for the circle. Okay, if we subdivide the entire circle the way we have here, it turns out we're going to have 64 subdivisions. We've divided each quadrant basically into 16 subdivisions. Let's start with the circle as it was originally constructed. We have 1, 2, 3, 4 points on the circle defined by the intersection of the x and, we can call it the x and the y axis, or the horizontal and the vertical axis. So I use purple to indicate those points. I'm using purple to circle the 4, and I'm going to use purple to emphasize the corresponding points on our graph. Okay, we've divided the circle equally. We've got 4 points that are equally spaced around the arc of the circle, and we've got 4 points. I missed one of them. Actually, it's 5 points. I'm kind of fudging. This first point is kind of automatic. We've got a point here, 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 and here. 1, 2, 3, and 4. And actually, if you count the points like this, this point doesn't really count, but if you continue going around the circle, we hit this point again, so I'm going to include it here. Okay, we've got 4 points on the circle. And I've marked 5 points here because the origin and the last point are kind of redundant. So in a sense, then we've got 4 plus 1 points on the circle, corresponding to the 4 points here, because we counted this point twice. Okay, well, if we now do one subdivision, how many points do we have? Well, if we subdivide each of these angles, as you've seen, we're going to get angles here, or points here, here, and if we reflect this one down here, we get one about here and one about here. So now we get the points that bisect these 4 segments on our horizontal axis on the corresponding graph. And wherever that bisector was, I guess it's probably here, then we bisect this segment. Could probably put, it's a little hard to see because optical effects, optical illusions involved with all the angles and everything else that's going on, but we get 4 new points. Okay, so now how many points do we have? Well, now we've got 8 points. And the new points are in blue. Okay, well, we subdivide again, and of course, you probably see where this is going. Okay, we subdivide now here, and where are we here? And here, and here, and here, and here, and here, and here. So how many new points? 1, 2, 3, 4, 5, 6, 7, 8 new points, which is going to give us a total of 16 points now that have been marked on the circle. And I'll put a red circle around that. Now I'm not going to mark the rest of the points, but it should be clear that if we now subdivide each of these angles, we're going to get 16. I could count them, 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 new points for a total of 32 points. And at that point, one more subdivision will get me down to the angles that I actually constructed here. There would be 64 around the circle. Meaning, of course, that if we do the construction, now we have 64 points on our sine function, on our sine graph. Now, if we continue this on, every time we increase the number of subdivisions by 1, it should be pretty clear now that the pattern is that we're going to double the number of points on the circle. Okay, so, well, I can say that, okay, 4 is 2 to the second, 8 is 2 to the third. Because, of course, 2 to the third is what we get if we double 2 to the second. And then if we double 2 to the third, which is, of course, 8, we're going to get 2 to the fourth. And that turns out to be 16. Here we have 2 to the fifth, 2 to the sixth. How do these exponents compare with the number of subdivisions? Well, obviously, every time the number of subdivisions goes up by 1, since we're doubling the number of points, the number of points on the circle is going to double, so the exponent is going to go up by 1. When the number of subdivisions is 0, the exponent is 2. If you think about it, you see then that the number of points on the circle is going to be 2 to the n plus 2 when we get up to the nth iteration of our subdivision. So I'm going to call that 2 to the n plus 2. Okay, just following this pattern, we're stuck. If there are n subdivisions, since the exponent is always going to be 2 greater than the number of subdivisions, we're going to have n plus 2, 2 to the n plus 2 points. Well, what does that tell us? How many points are we going to get? Well, if we do 10 subdivisions, so I'll say iterating the subdivision 10 times, we get 2 to the 10 plus 2 equals 2 to the 12th points on our graph. That's 4,096 points. And you can figure it out yourself. In the first place, 4,096 points here, if I make them with chalk, is going to give us something that appears to be just a smooth curve. There's not going to be any distance between the chalk points. I mean, if I do a chalk point here and a chalk point here and here and here, that's 4 chalk points that really look like part of a more or less straight line if I'd have been able to locate them more accurately. Okay, so just 4 points gives us this much line. 4,096 points would give us 1,000 times that much line, and that would be a whole lot longer than the arc, or than the distance we travel along this curve. Distance we travel along this curve might be a few hundred points. And in a few hundred, the points would probably be even closer than these, giving us even a smoother line. So what I want to say about this is that as n increases, the number of our graph, if we just plot a dot for every point, our graph becomes dense with points. Okay, so I'll say here, the graph is already dense. Enough to form a continuous or let's say form a smooth chalk line if we have 4,096 points. And I'm going to make a further statement, and I'm talking about now a topological concept that's not all that deep unless you try to apply it to arbitrary topological spaces, but it's still pretty deep. It's a pretty deep result in analysis, top topology analysis. They kind of share a lot of ideas. Okay, a lot of definitions and so forth. The topological aspect of this, and you don't have to know what I mean by topological, I'm just throwing out the word, is that in the limit, as n approaches infinity, no matter how small you make your dots, they're going to be dense and you're going to get a smooth curve. And in the limit as n approaches infinity, even points with 0 dimension will form a continuous smooth line with no breaks in between them, even though there really are breaks in between them. There's a contradiction you can start to wrestle with now if you want to, but we'll try to make a little sense of it as we go. So, I'm just going to say, as n approaches infinity, the graph approaches topological density, and I don't think any mathematician really uses density to refer to topological density, but right now when we're just working intuitively, I think we can get away with using that intuitive ideal. Okay? And topological density means no space between constructed points. Okay. Now that doesn't mean we have every possible point on this graph. So I'll say however, there exist points on the curve which will still not have been constructed. And never will be. And we'll develop this idea just a little bit.